Okay, everybody, welcome to class. Hope you had an awesome Thanksgiving break and ate lots of turkey or turkey substitute for those so inclined. Today we'll go over our learning objectives, okay? We're going to talk about the temperature dependence of our carrier concentration. So the number of carriers, be they holes or electrons, what do they do as you change temperature? We're going to talk about Hall measurements as a way to determine the carrier concentration. We're going to dive into at least like a qualitative explanation of how a whole bunch of different semiconductor devices work. Things like MOSFETs, transistors, PN junctions, things you've probably heard at least mentioned before. We're going to try and qualitatively describe what's happening with our, albeit limited understanding of band diagrams. We can actually explain most of what's going on. By the end of class, we're going to talk about how ceramics and polymers can be made to conduct electricity, which is pretty wild. And if we have time, we'll get into dielectric materials. So let's pick up where we left off last time. Last time we said that you can have silicon, and if it's just pure silicon, then each silicon's got 4 electrons. It bonds with 4 other silicons. All of a sudden, all the silicons have 8 electrons, which is really just a way of saying that their valence band is like completely filled, right? The electrons fill right to the top of this valence band, and so there's no empty seats here, and there's a band gap before you get to those upper ones, and so it's not particularly conductive. Intrinsic silicon is not a good conductor of electricity, right? You have to heat it way up. You have to give it lots of thermal energy before they start jumping that gap and conducting. But we said you can dope it. You can dope it with either donors of electrons or acceptors, and we've drawn here one of both. If we've given it donors, that's something like phosphorus, which has an extra electron. And that electron, while phosphorus does technically want to hang on to it, it doesn't want to hang on very badly. If you give it a little bit of electric field, it will strip it away. A little bit of thermal energy and electric field, and it will strip this electron away, and it will jump a small gap and now be in the conduction band where it can conduct electricity. That's an example of an electron donor, right? Or you could do an electron acceptor, something like aluminum or boron, that has an empty seat for an electron. So the electron here from your silicon band can hop up and occupy that seat, right? And again, that takes a little bit of energy because now this impurity ion becomes negatively charged, right? It has one extra electron than it would normally like to have. But you create a vacancy in this valence band, which can now travel. So both of those methods can be used to increase your number of your carriers in your semiconductor, either p-type or n-type. P-type means it has holes. N-type means you gave it extra electrons, okay? And because you can dope it to have extra holes or electrons, we modified our expression, right? We said in one case, let's say if it's n-type, then the number of electrons that you've doped it to have, that number is much, much higher than your number of intrinsic electrons, the ones that jump the gap on their own. And that's also much higher than the number of p holes which were present due to doping, okay? And because of that, you can basically ignore the contributions of these two, and your conductivity expression can be written just as this. Your number of electrons times the charge of that electron times its mobility, okay? If this was doped p-type, then you could ignore this part, and you'd only care about that part, okay? Any questions about that from last class? About recapping this? Okay, let's keep going then. Okay, so as you heat things up in semiconductors, you're giving it more thermal energy. What should your carrier concentration do? It should increase, right? You're giving it more and more thermal energy, more and more of those electrons, a higher fraction can start to jump that gap. So if you were to plot Ni, that's your intrinsic carrier concentrations, the ones that come about by jumping the gap, as a function of temperature, they really start to take off, right? You get more and more. These are orders of magnitude increases, right? So 100 degrees can give you an order of magnitude or a little bit more in increase. So you really start to get more and more carriers as you heat these things up. Therefore, turn to your neighbor and say, what should the conductivity do for a semiconductor as you heat it up? Okay. Up or down? Does it go up or down? It's definitely going to go up. A semiconductor is going to go up in conductivity, right? So it might look something like, let's do a different color. It's going to go up. And the reason why is because we go back to our expression for conductivity, electrical conductivity, is directly proportional to the number of carriers we have. More carriers, better conductivity. Now, what about this mobility term? Didn't we just say a couple classes ago with metals that the mobility goes down with temperature? Things start to vibrate more and more, and your mobility goes down. It's also true with semiconductors. Your mobility also goes down. But here you're seeing orders of magnitude increase in your carrier concentration, and this only goes down by less than orders of magnitude. So this term suffers, but this one gets so much better that overall you see a net rise in your conductivity with respect to temperature. How would a metal look? If you were going to sketch this, how would a metal look on the same plot? First off, is it above or below the semiconductor? Definitely above. The metal conducts. And then what trend does it have? It's going to be a negative trend, right? Because there you have tons and tons of carriers, and you're not relying on thermal energy to give you those carriers. They exist because it's in the middle of a partially filled band, so you're not relying on jumping a band gap. So you don't need that thermal energy. So the only thing thermal energy is doing for you with a metal is reducing your mobility. So you've got these two different trends. So if I gave you a plot like that on a final exam and I said label the metal, label the semiconductor, and explain the behavior, it has all to do with mobility versus thermally activated carriers. Any questions? Okay, let's keep going. Something that we will talk about a little bit is that the number of your intrinsic carriers, n sub I, since it's a function of your thermal energy and this gap that it has to overcome. Remember, you've got this filled valence band, and you've got this totally empty conduction band. And if you give them enough energy, they'll hop that gap. That's an energy barrier, right? That gap, you can think of it like an energy barrier, and therefore, the hotter you get it, the more likely you're going to be able to jump that gap. Therefore, we can write this sort of as an Arrhenius-style equation, just like we've seen all semester long. Your number of carriers is going to be proportional to some constant, let's just call it n, but then it's going to be an exponential of not an activation energy, but your band gap. Your band gap is the activation energy that you have to overcome, divided by your thermal energy. Now, the factor of 2 comes in for reasons that we won't get into in this class, but you can see that you can treat it a lot like diffusion. If you've got a big activation energy for diffusion, you don't get very good diffusion. If you had a really big band gap, you don't get a lot of carriers. It's the same sort of approach, okay? How about this? We'll do a clicker question. Okay. The clicker question is as follows. It says, an extrinsic semiconductor is going to increase in electrical conductivity with increasing temperature over all temperature ranges. True or false? Extrinsic means that we've doped it. So we're not relying on thermal carriers for the majority of our carriers. The majority of our carriers come from however we doped it. If we gave it 10% phosphorus, that tells you exactly how many electrons or holes you're going to have. It comes from the dopant. Okay, get your answers in. Another 20, 30 seconds. Okay, I'm going to close it. Everyone looks like they've answered. Okay, what do people think? Most people think false, that it will not increase over the whole range. So I actually made this one correct for either answer, because technically it is true is the right answer, but you could argue it either way. So you got full points no matter what you put in. Somebody argue both ways for me. If you thought it was false, give me your rationale. Somebody that voted false. What do you think, Ashton?
Because the things you're doping into it, I figured that those are metals or non-metals, they have more, they could be decreasing their conductivity when it heats up.
So you dope in something like phosphorus or aluminum. Okay, and say what again?
And because they're a metal, their conductivity goes down with...
Oh, okay. So you're thinking sort of like a rule of mixtures. If you add 10% of a metal, maybe that will... Okay, that's an interesting way of thinking. That's not quite correct. That's an interesting way of thinking it. Other ideas? Why is it the case that it shouldn't be the same overall temperatures? Or was it should? Which one was false? Let me remind myself. False means you said an extrinsic semiconductor will not increase over all temperature ranges. That's your argument. So what's the argument there? Why would it not increase over all temperature ranges? Or let's think of it the other way. Why would it be true that it should increase over all temperature ranges? Nobody? Everyone, 96 people just said, I'm just going with my gut, but I don't know why. It's not entirely encouraging. Okay, let's think about it. So let me ask you this. The phosphorus, it had those 5 valence electrons. Now, in a perfect world, it would keep all 5 of those electrons. But in the real world, it says, I really only want 4 of those, and the 5th one is like, take it or leave it, right? It's like the child that, like, it didn't really want it. It's like, you can go if you want. Like I feel about my 3-year-old sometimes. I'm allowed to say that because I have a 3-year-old. Right? Sometimes I'm like, go ahead, go it. Right? So it technically did take a little bit of energy. And so if you went all the way down to 0 Kelvin, that 5th electron can't escape. Right? So you technically do need a little bit of energy to even ionize your donor or your acceptor. Right? To ionize, it means you give away or you take that extra electron. Okay? Now, so that gives rise to a plot that looks like this. Let's sketch this. Okay? The plot looks something like this. As a function of temperature, here's your carrier concentration, either N or P-type. If you go down to really low temperatures, your carrier concentration is going to fall off to 0. Right? There's no thermal energy. You can't strip away that extra electron, or you can't make it take an extra electron. Okay? Okay, so there's this first regime. And then, once you give it enough energy to take that electron away, or to give it an extra electron, you've got this region where it's basically flat. You've got this flat region. And then if you get to really high temperatures, you're going to see another rise again. Right? The reason why it starts to rise over here is if I was going to sketch this. This is the plot for N sub I. That's your intrinsic carrier concentration. So if you keep on heating something up, your intrinsic carrier concentration starts to take off and explode. Right? And it will actually surpass the dopant that you added. So this point right here, this value where it's at over this middle region, that's at the doped value, right? So this is what a typical extrinsic versus intrinsic semiconductor carrier concentration plot looks like. Okay? Any questions on this? Yeah, Josh?
So since the extrinsic area is where it's plateaued, does that mean that the temperature increase doesn't actually increase?
Yeah. Typically this is on a log plot, and so on a log plot that looks like it's totally flat. But we know that your overall conductivity includes both intrinsic and extrinsic contributions. So technically, because this is rising, you are getting slightly more conductive. But on a log plot, it looks basically flat. That's why I gave you credit no matter which way you answered this. Because in this region, it looks like, hey, it looks like it's flat. But in fact, your intrinsic is slightly increasing. But that contribution is dwarfed by your extrinsic one. So it's not it'd be like saying you're at a baseline of 1,000,000, but you're steadily increasing by like 1 each time. 1,000,001, 1,000,002. It doesn't look like you're changing very much, but technically you are. That's what's happening there in that middle region. Okay? So because of that, we can name these 3 regions, and I think they're labeled on this plot. Let's just label them here. So the lowest region, we call that freeze out. We freeze out all of our carriers if you go to a too low of a temperature, right? Then you've got your extrinsic region, where the conductivity is dominated by however you doped it extrinsically. And then over here you've got your intrinsic region, where even if it is doped, you don't care, it gets dominated by your intrinsic contributions at high enough temperatures. Any questions on this? Okay. So again, on a log plot, it would look something like that. You can see that they initially started this thing. They doped it with different amounts of acceptors. So this would be something like boron or aluminum that they doped it with. The initial concentration of donors, so this was doped with 2 things. It was initially doped with donors at 10 to the 17th per centimeter cubed, right? So it was doped with something like 10 to the 17th of phosphorus. And then they also doped it with acceptors, right? something like boron or aluminum. And as they change the concentration of acceptors, you see that the extrinsic region reaches different values, right? If you don't have very many acceptors, then in this region, the number of acceptors is way less than your donors. You have this really low conductivity. If you have lots and lots of acceptors up to really high numbers, it's going to get higher up there, right? But in either case, no matter how you dope it, at high temperatures, extrinsic is going to take over at high temperatures. No questions? Clear as could be? Okay. All right, so we've got freeze out, extrinsic, and intrinsic. As we said, your mobility is influenced, right? As you heat things up, the mobility does go down. And as you dope it, your mobility changes too. So on this y-axis, this is your mobility of electrons or holes. And on this side, this is your carrier concentration. So as you were to dope something to add more and more, say, aluminum atoms, your mobility, this is for boron and phosphorus and arsenic, excuse me. In all of these cases, your mobility goes down as you dope it because you're going from a nice pure silicon lattice that electrons and holes can sort of whiz through with ease, and you're adding more and more impurities, which have strain fields, and all these things are going to restrict the ability for your electrical carriers to move through the lattice, right? So it's not so bad up until a certain point, and then it really falls off, but then it doesn't really get much worse, right? Even if you really heavily dope it, you're not getting much worse. It's like it's already as bad as it's going to get, right? But your mobility will change as you dope things, okay? All right, and temperature does the same thing. Your mobility goes down as a function of these higher temperatures. It goes up initially because reasons we won't get into this class. Okay? All right. Regardless, once you dope something, and how do they dope things, by the way? Anybody work at IM Flash, do an internship there? How do you dope a semiconductor? We keep on saying, like, put aluminum in there, put phosphorus in there, but how do they do that? How would you do that? Maybe turn to a neighbor. How would you get those atoms into your material? Okay, how would you do it? You've got pure silicon. You need to dope it with phosphorus. How are you going to do it? What do you think? What would you do?
Heat it up and diffuse it.
So what do? You're going to heat up what? Both those things? Just one? Just the other? What are you going to do?
Just one.
Okay, you heat up just the silicon, and then what do you do with the phosphorus?
Integrate it in. I don't remember.
How are you going to integrate it? These are questions that you guys will face soon in industry if you go work in semiconductors. What do you think in the red jacket?
We do metal diffusion.
Metal diffusion. How do you do that? Is that like the diffusion couple that we talked about a couple chapters ago? Where you just put them next to each other and let them sort of do their thing? That's one option. They do that. They literally paint it on the surface of the silicon. That's one thing they do. In fact, you can mask your silicon. Anybody do lithography? Anybody aware of how this works roughly? This is pretty rad. We're going to get to this in a minute, but let me show you a quick picture of how photolithography. So when they create circuits that have these really intricate patterns, come on, Google. You know what I mean. They do this. They start out with this. That's terrible. Right? They start out with the silicon substrate up here, and it might have an oxide on the surface that you don't like. It might have silicon oxide there. So the first thing they do is they'll put a photoresist on top of that. A photoresist means that when you shine light on it, with the presence of a mask, the light will only see certain parts of your photoresist, right? And there's both positive and negative types of photoresist. If it's a positive one or negative, it tells you whether or not this resist is going to set up and become hard or stay a liquid. Because initially it's sort of in like a liquid gel state, where if you rinsed it, it would rinse right off. So if you shine light on it, maybe in this case it becomes hard. It sets up like a jello. It becomes more rigid, and everything else would wash away. So when you take the mask off and the light off, everything washes away except for those regions. Or it might be the opposite, where it's basically set up, but if you shine light on it, it breaks up that photoresist. In either case, it allows you to put channels on it and use light to write those channels. What's so great about that? We know how to magnify and focus light. So you can do itty-bitty tiny channels by just sending your light through lenses, right? And on certain pathways, you're now going to have a pathway to the silicon underneath. The first thing you have to do, though, is you're going to have to etch away this oxide layer. If you didn't do it originally, you're going to have to do it afterwards. So you've got like this region where now you've got a path to the silicon underneath, right? They might put another mask on top of that, depending on what they're doing. But now's when you could deposit your phosphorus or whatever else, right? You could put it in a sputtering system where the silicon's sitting inside a chamber, and you heat up the phosphorus, and it ejects phosphorus atoms onto the surface of this. You might just rinse a solution over it, and it's going to sit on the surface, right? But you're going to do something to put your dopants in a certain spot on your crystal, so only certain parts of your silicon conduct electricity. And the rest of it doesn't conduct very well because it's just intrinsic silicon. And when you wipe all the stuff off the top of it, now you've got channels, right? So let's see if we can see a picture of that. What do we got? So you can generate very unsatisfactory images here. Something like this. So like this is what it actually looks like. You can actually, here's your photoresist, right? You wash that away. Now you've got this channel. You could put your silicon here, or your dopants here in these channels. And now you have whole channels running through your material that have different conductivity than the stuff around it. And this is how they start making really interesting electronics devices. It all had to do with light, right? We're going to get to how we got to doing that in a minute. Okay? So they heat it up. They'll paint it on the surface. They'll sputter it. There's something called ion injection, where they take ions like phosphorus or boron, they ionize them, they put a big electric field between your substrate and some cathode material, and then they bombard them into your sample. They just crash them into it. So all these have sort of pros and cons in the sort of distribution that you get. We learned last chapter this. We said that if you were to take a concentration profile where you initially have some level at the surface and you heat it up, it's going to be non-steady state diffusion. So the concentration profile of your dopant species is going to look something like this. So that means that your conductivity is changing as a function of depth. So maybe there's like a minimum threshold that you have to get to. So you could tie back to the diffusion stuff that we learned about last chapter and say, I know the diffusion coefficient for this material. I know the temperature I'm taking it to. I know how deep I need it to go. I know exactly how long it has to be in the furnace to get that minimum conductivity. Right? It ties all these things together we've been learning about. Okay? So how do you actually measure your concentration of your carriers? You do something called the Hall effect, or a Hall measurement. And to me, this is a little bit crazy that this actually works, right? You take your Hall bar, which is just a rectangular sample of your material, and you're going to pass a current through it end to end. So you take a battery, right, and you hook leads up to the ends of this thing, and you're going to pass a current through it. If the current's traveling that way, that means your electrons are traveling that way. They travel opposite directions. Current and electricity are opposite directions. Now, if you apply an electric field to this, a magnetic field to this, if there's a magnetic field in this, your battery or magnets on top and bottom of it, then a charged particle moving in the presence of an electric field, the current's this way. If the magnetic field is going, say, the up direction, then your electron, right-hand rule, will travel that way. You literally get your electrons migrating to the left-hand side of this bar. Right? So if you had another multimeter and you're measuring the voltage distance across this thing, you have electrons traveling over here that's going to build up a negative charge. You can measure a voltage across this thing in the presence of a magnetic field. That seems kind of crazy that actually works. And from that voltage, what's called the Hall voltage, this VH right there, that Hall voltage, if you know what the magnetic field was and you've calibrated this, you know what the current was, you can back out exactly what the carrier concentration is in your material. Right? And that's really the best way to measure it. There's another way that they do Hall measurements optically, but I'm not as familiar with them. This is certainly the more common one. So again, the Hall voltage that you measure in this lateral direction across your sample is equal to the Hall coefficient. That's where your electron concentration is going to come out. Current, magnetic field, and obviously the thickness of your sample. Okay? So I think you'll have an example to do this on one of the homeworks this week. The Hall coefficient is just 1 over the concentration of your carriers times their charge. That's the Hall measurement. Any questions on the Hall measurement, on how we get carrier concentration out of that? Okay, let's keep moving then. All right, let's talk about some basic devices. We've shown you semiconductors, and all we've really said, like, it all boils down to the fact that a metal... A metal doesn't have a band gap, and a semiconductor does have a band gap. So how can we... Dude, we've got the volume like to the max on this microphone. That's a little better. Okay. So how is it that you can take something that has a band gap or not and create all the crazy devices that we have? Things like transistors, things like PN junctions, solar cells. How do all these things work? So let's start with a rectifying junction. A PN rectifying junction. What does this do? It takes an AC signal and it turns it into a DC signal, right? So, okay, that's working. So if your input signal was something like this red curve, you're going to run it through this PN rectifying junction, and the output signal would maybe only be the positive portion of that. Okay? It's only the positive portion. How on earth do we do that with what we've learned about in this class? So we're going to start with the PN junction. And my PhD advisor used to always say that humanity has stumbled across like 3 amazing inventions. Like fusion, pretty amazing, the PN junction, and the third thing I forgot. I'm sure it was awesome too, right? Nuclear energy is pretty amazing. The PN junction, though, is right up there with it, right? Here's how it works. If you've got 2 materials, one's P-type, one N-type, we're going to smush them until they touch, right? So you've got one right here and one right here. If this is the N-type material, and this is the P-type material, the N-type has the Fermi level closer to that, closer to the conduction band, sorry. Whereas the P-type, it's closer to there. This has an excess of electrons, N, whereas this has an excess of holes right there. If you bring those together until they touch, what's going to happen is this Fermi level has to be continuous. It has to become a flat line. So the only way that that can become a flat line when they're at different energy levels is something called band bending. Okay? So let's draw it. This was before. Now after this line has to be constant. So you've got your N-type material here. Let me just get rid of that. It's going to switch and it's going to look like this. See that? On the left-hand side, it still looks like our N-type material. On the right-hand side, it still looks like our P-type material. But in between, we've got this sort of funny business happening, right? The PN junction makes so many things happen that we care about. Remember, in this case, we've got lots of electrons up here. In this case, we've got lots of holes in the valence band, right? So what will happen, I want you to turn to your neighbor and describe what will happen if you pass an electrical current through this material such that the electrons travel that way. If the electrons travel that way, and the holes travel that way, what will happen? Go ahead, turn to your neighbor and discuss. Okay, if you select a voltage and you apply a voltage across this PN junction such that electrons travel to the right and holes travel to the left, what happens, Andrew? What do you think? Just take a guess. Oh, it's on YouTube? Okay, anybody have a thought? What might happen? Josh? Could they jump? Well, think here. Here you've got these extra electrons, right? And here's a bunch of spots for electrons, right? Holes. So if you force these to go this way, you're moving this up the energy gradient. It's going up in terms of energy as these things travel up. Well, these guys up here are going to say, there's a better gig for me if I just drop down and fill these, right? And so they will. They will travel up this gradient, but when they're up there, get blue again. When they get up there, they're going to say, why am I at this higher energy level? If I can, I'm just going to fall back down and fill that spot. When it falls back down, energy has to be conserved. Since it went down in energy, it has to give off energy. And the energy that it gives off is what? Light. You get a photon coming off of this thing. We just created an LED. This is an LED. An LED gives off a light of a very specific color, right? How does it do that? They chose a material that has a band gap, which equals, in energy, the color of light that you want to get out. And then they intentionally drive current up this energy hill and allow these things to fall back down and occupy these, right? Or conversely, you could imagine a hole going this way. Since it's a hole sort of the opposite, this is actually going down in energy for it. Electrons are easier to think of, right? You created an LED. anybody who's taken ECE, you know that LEDs only work when you wire them up one direction, right? There's like the positive and negative side, and you can't reverse those. Well, why? Somebody explain to me why I can only wire this up one way to get current flow through it. Or let me ask you this way. What we just described, will you get electrical current out of that? No, because the electrons couldn't make it all the way through, because they said rather than traveling all the way through and completing your circuit, they're just going to fall down and recombine and create light. So you get no current flow in one direction. But if you go the other direction, if you move electrons this way, they got no problem. Holes going that way, no problem. Nothing happens. There's no recombination. So depending on the polarity, you get current or you don't get current. So that's exactly what's happening here. A PN rectifying junction will only allow the passage of current in one direction. So maybe only the positive component, right? The negative will turn into light. And then positive will pass current, the negative will turn into light. Josh?
So going in a direction, and if one direction is electricity creating current, the other is the photovoltaic, is light turning into electricity?
That's exactly right. Yeah. In one case, you get a passage of current with some resistance. It's not like these things are infinitely conductive. Think of it like a resistor, right? And the other way, you get no conduction of current until you cross over a certain limit, and instead you get light. What happens if you go to too high of a voltage? LED, what do they call it? Breakdown? I think they call it breakdown voltage. Let's see what comes up. Yeah, if you bias it too much, let's see, let's find a better picture. So, something like this. Okay? If you go in one direction, you get lots of current, no problem. Okay? The other direction, you get no current for the most part. There's always a little bit of leakage current. A little bit does trickle through. But if you go over a certain point, bam, you get breakdown, and you get a lot of current happening there. What's happening there, we'll get to probably the beginning of next class, not today. Okay? But here's our first, honestly, the most important thing that we're going to talk about for having this whole class is this PN junction. And it's really pretty simple. You took two different types of semiconductor materials, you doped them different ways, you smash them together, and all of a sudden we can make all sorts of stuff. This is a solar cell, by the way. This is a solar cell, right? It doesn't look like it yet, but this is a solar cell. How is this a solar cell? It's just operating in reverse. Instead of driving it with electrical current up this energy hill and causing light to come off, what if light comes in, right? Light comes in, it hits one of these holes, and gives it enough energy by absorbing that sunlight that this thing temporarily gets jumped up there, and then it's able to move, right? If it travels in one direction, you get annihilation. If it travels in the other direction, you can complete your circuit, right? So this is all that is to a solar cell. A solar panel, all they have to have is a PN junction built into it. So you'll hear oftentimes like the absorber layer, collector layer. If we go to PV, absorb, collect, it'll show you different layers, but all these layers are PN junctions, right? So let's take a look at one. Okay, so this is a complicated one, but let's look at it. Okay, so the top you've got your contact, you've got ARC, that's going to be something that light can travel through, but it's going to be your current collector. So it can be like a grid of platinum wires, they do that, or silver wires. Here's your top cell, that's gallium indium phosphate. Then you've got the tunneling junction, you've got a middle cell and a bottom cell. What they've done here, this is called a hetero junction or a heterocell. They've taken and they've intentionally designed it to absorb light at different regions of the solar spectrum, right? So your red layer, for example, it's going to have some band gap. It has a band gap of 0.67. So it's only going to absorb your really low energy light. Long wavelength is low energy. It'll absorb this stuff. Now the middle layer has a different band gap. It's 1.4 electron volts. So it's going to absorb in this region. And then that top one, it's 1.8 electrons. So it's going to absorb this stuff. So think about it. Light that's coming in, that's low energy light, it's transparent to these two materials. It doesn't have enough energy to promote their electrons up to the conduction band, so it just travels right through them. It doesn't even care about them. But when it gets to this one, it absorbs. So these solar cells are currently the most efficient, but they're also the most expensive. They're the most efficient because they're capturing the entire solar spectrum, which looks like this, right? Here's your intensity of light coming as a function of wavelength from the sun. The most efficient solar cells will capture all of this, right? So by having three different junctions, you're capturing sort of three different regions by tuning all the different parts of the solar cell. Now, that's not the most common one because this is expensive. As you can imagine, putting all these different junctions together, is expensive, and it also has reliability and other issues. So by far the most common solar cells, they compromise. There's something like, what's this? Where it's just, here's your PV, right? You've got your absorber layer and your emitter layer. We're going to show those in a minute. They basically absorb just one section of the sunlight, but you can make them for relatively cheap. They're definitely not absorbing your entire solar panel. That's why if you've ever touched like the back of a solar panel, even though it's absorbing some of that sunlight energy, it also gets hot from the sun. Because a ton of the energy just goes straight through to the back surface where it gets absorbed by the metal layer on the back, which is usually molybdenum or something. Okay? Any questions on photovoltaics on this main principle? Yeah, Andrew?
Yeah, so is that process finite dependent on the amount of material you have?
Yeah, absolutely. So light will travel, like in this picture, we sort of said like, oh, okay, if your energy of your sunlight is anything above 0.67, this is going to absorb it. But of course, it's a function of depth, right? As you make this thing thicker and thicker and thicker, it's going to absorb more of it. If it's really, really thin, like these so-called tunnel junctions, if it's really thin, technically it should absorb it, but it doesn't absorb it fast enough, and so a lot of the light trickles through it. It tunnels through, right? So to make an effective solar cell, you have to balance amount of material versus thickness, which is probably related to cost, right? So there's all these things you have to balance, but at the heart of solar cells is just a p-n junction. All you've done is you've created one of these, right? And light comes in, it goes up, and then you actually want it to get absorbed in this middle region, and then it gets depleted. Because you don't want recombination to occur. You don't want a solar cell to absorb light and then just become an LED and give that light right back off by these things falling back down and recombining. So you want this what's called a depletion region to exist. You want your charges to get generated in this region and then to get swept away to the sides, right? And the ability for it to do that can be sort of designed on how thick you make that region. So I'm not going to go into more depth on this. There's great classes you can take here at the U. A guy in my department, Mike Scarpula, teaches a class on semiconductor devices. You'll learn all you want and then some about these if you want. But this is it, right? These are solar panels, right? You generate your carriers in the middle. This is actually creating an LED, but it's the exact same layout for a solar panel. Okay, what about a transistor? You've all heard of a transistor before. How does a transistor work? Well, anybody that's played guitar, right? If you play guitar and you use an electric amplifier, these are like, you might have even heard like a tube amplifier, right? In the early days, the transistors that they used were not the same modern ones we use nowadays. Actually, you can still go buy tube amplifiers. But what it does, it takes the signal from your guitar and you want to amplify it to be a loud noise that you can run through a speaker, right? So how do you do that, right? How do you generate the signal in the first place? Any guitar people in here? How do you generate the electrical signal in the very first place on a guitar? You've heard of pickups before. The pickups pick up the electrical signal. How do they do that? Typically, there's different ways. There's some that rely on the pressure variation, but they're not the best ones. The better ones rely on magnetic strings. If your strings have cobalt in them, they're slightly magnetic. Therefore, as they vibrate, there creates a very small current, right, as they move. And you have an electromagnetic sensor, right? In any case, your signal comes in and it's quite small. If you just took your guitar and plugged it into a speaker directly, you're not going to get a lot of noise out of that because the pickups don't generate a very big signal. A transistor is something that can amplify that signal, right? So how do they work? Okay, so you've got your emitter, your base, and your collector. And all these are PNP junctions or NPN junctions. You're just going to put together those PN junctions, right? In one case, you've got this one. You've got an N-type material with lots of electrons. In the P-type material, you should have an excess of holes. And then you've got your P-type material, or N-type over here. The key thing is that you bias a voltage between these two. You apply an electric voltage between these two that's big. And because it's big, you get this big difference in energy as you go there, right? So what happens? As you pass electrons through this system, okay, technically when you go from N-type to P-type, you should get recombination. You should have created an LED, right? A tube amplifier is kind of what's happening here, right? You're creating light on these things, right? But if some of them do get through this P region because it's thin, and when you see diagrams, it's always drawn very thin. As your electrons travel through, some will recombine here, but the ones that make it through, they drop way down in energy. That translates to a larger voltage, right? So your signal gets amplified. Instead of having a small amplitude, it gets really amplified, right? And it's just because you put together a PNP or an NPN junction, right? So the key to making this work, we're not creating energy out of nowhere. You had to apply a big voltage across it. That's why, so this is like a small voltage generated by your guitar. This would be millivolts probably. But you apply volts here, right? 120 volts out of your wall or something. There's a big difference in voltage here. So the electrons that do squeak through really get amplified. Any questions so far? And I don't care if you understand this perfectly. I just want like big picture to connect the band diagrams we've talked about to devices you might care about. Let's do another one. How about a MOSFET? Anybody heard the word MOSFET before? Like MOSFET speakers? Nobody? Nobody cares about speakers in their cars anymore. Right? How do they work? Right? A MOSFET transistor has, the word stands for metal oxide semiconductor field effect transistor, MOSFET, right? So, as the name suggests, you're going to have a metal, you're going to have an oxide, you're going to have a semiconductor, you're going to generate a field effect, right? So what is all happening here, right? So let's say you start out with a P-type substrate. So you took your silicon and you doped it uniformly everywhere P-type, right? Something like boron or aluminum, all over the place. So lots of holes in here. Then you take certain channels using photolithography that we talked about, you make them N-type. So you put maybe some phosphorus, I said it the other way. Now you put something like phosphorus here, something like boron here, okay? So now you've got regions that conduct electrons and regions that have excess holes, okay? Now, for a transistor to work, you want it to operate only under certain conditions. This is how they store solid-state memory. When the charge is there, right, there's memory there. Or in a transistor, you don't want electrons to be able to travel from source to drain unless a certain condition is met. That condition is if there's a voltage applied across this. So this is your metal, excuse me. Metal conducts electricity, no problem. But you put a metal oxide here, and the oxide typically does not conduct electricity. It's got a big band gap. So electrons won't travel from here to here. Instead, you build up a voltage. If you put lots of electrons here, let's see, we want to go the other way. We want to put lots of positive charge here. If you put a bunch of positive charge there on this surface, then you create a bunch of negative charge here to compensate it. A bunch of negative charge here. And a bunch of negative charge here is the same as making a thin little region right here, N-type. You gathered a bunch of electrons right at the surface of that. So the electrons that normally, if you tried to pass electrical current, electrons from here to there, they would reach the P-type region and annihilate. You get no current. All of a sudden, if you apply a voltage to this in such a way that you pile up negative electrons here, there's a tiny little pathway, like a road, that your electrons can travel on. It seemed like science fiction. This is amazing. This is really cool that they came up with this, right? All of a sudden, you have like a road that you can turn on and off. Electrons can travel from here to here only when you want them to. So you can write sections of your memory only when you want it to, and you can rewrite it only when you want it to, right? So this is a MOSFET transistor. They called it transistor the same before because before you had this emitter, base, and collector. You've got your emitter, base, and collector, right? So here you've got your source and drain. That's like your emitter and your collector. And then your middle and the base, that's going to be the metal oxide one, okay? So you connect this to 3 electrical pathways, and you can decide whether or not current passes through here, okay? You guys don't seem amazed. This is amazing. Okay? With transistors, once you've got PN junctions and transistors, you can make everything, right? There's other stuff we need. We need capacitors, which we'll get to later this chapter. But, I mean, that's the bulk of all your different things in your electronics toolkit. When you take ECE and there's all these little devices in there, they're just different combinations of transistors for the most part, right? So all these complicated, maybe you learned about these in ECE, like OR gates, AND gates, NAND gates, NOT gates. All these are different combinations of your transistors put together in different ways that now computers can do logic operations like plus or multiply or this or that or only these two things. Like all those logic operations are based off of whether or not electricity passes through channels. All of that. That's amazing. Right? So where did this all get started? Forgive a brief aside here because I think it's one of the coolest things that ever happened. In 1959, before any of us were around, Richard Feynman, a famous physicist on the Manhattan Project, part of the atomic bomb, all that, he gave a lecture at the APS meeting. APS is American Physical Society. And this is like one of these epic, everyone knows about it lectures in science. It's called Plenty of Room at the Bottom. Plenty of Room at the Bottom, he essentially said, we're thinking too big. we need to think smaller, right? He was like the original Ant-Man, right? He's like, there's so much room down there. Why are we not doing things with very few numbers of atoms? Why are we not miniaturizing and shrinking our electronics to tiny scales? You all seen pictures of supercomputers in the early days. They were like the size of this auditorium because they couldn't miniaturize things yet. And he said in 1959, enough of that nonsense. Let's get miniaturizing things, right? And so he offered a prize. He said, I'll give some amount of money, $1,000, right? Still wasn't very much even in the 50s. But still, he said $1,000 if you... There's two challenges. The first one was a micromechanical machine. A machine that had to be like a certain size or something. And the other one was to write a story on the head of a pin. Write a page of a book on the head of a pin. So the first guy who technically won the prize, and he paid him out, was this guy, William McLennan, and he was a watchmaker. So working with like tiny objects was like his jam. So he kind of cheated because he used like existing technology, and technically, yeah, he did write a few letters, but it was a technicality. It wasn't this quantum leap in doing things a completely different way that Feynman was looking for. And then later, this is amazing, Tom Newman. This guy was a grad student. It wasn't his advisor. You know, Stanford gets all his praise. They hire these amazing professors. It wasn't the professor. It was the student who said, what if we try, like if you're going to do something that small, you have to have really careful control of it. What do we know how to control carefully? We know how to control voltages really carefully. So they took an electron beam, just like the electron microscope that we showed you a few chapters ago, right, that rasters across the surface and creates the image. He used one of those, but he just left the beam on the spot for a while so that it would like damage the material, it would locally melt it or destroy it a little bit. And he, by applying a voltage carefully in both the X and Y directions, he could make that beam move a little bit. And he wrote A Tale of Two Cities on the tip of a pen. If you zoom in on that, right there, you say, it was the best of times. It was the worst of times, right? He wrote that with an electron microscope, right? And this was the dawn of the nano era, the era in which we all now enjoy the devices because they're miniaturized. We have, like, I don't even know how much memory is on this phone. Some stupid amount of memory, billions and billions of bytes on this thing, because we know how to write things in miniature, either using light, or in this case, they used a beam of electrons, right? So lithography, E-beam lithography, atomic probes, all of this is due to miniaturization that Feynman inspired in us not even that long ago, right? And because of that, you've seen something called Moore's Law. Have you heard of Moore's Law before? Some people? Moore's Law says two things. It says, what is it? Okay, there will be a doubling of the number of transistors for every 2 years, and something about the cost as well. The doubling is the main one, though, meaning on a per area chip, per area, we're going to double the number of transistors that we can fit on that. Transistors might be something like this MOSFET. So you have to find a way to shrink this whole architecture smaller and smaller and smaller. And in doing so, you can store more memory in smaller and smaller areas. And Moore's Law, we've been actually holding to it. It's actually slowing down. Instead of every 2 years of that number doubling, it's gotten to every 3 years. And now it's getting to the point where we almost have, I mean, we don't have individual atom gates, but we have what's called the 5 nanometer transistor. 5 nanometer means that distance between source and drain, whichever you want to type which one it is, this distance is 5 nanometers. That's like 50 atoms or something? That is not very wide. That's how small we can do it, right? Now, it gets to a point where if you have a voltage across that thing and the distance gets really small, those of you that have taken quantum, physics, you've learned about tunneling, right? When there's an energy barrier, right, which this technically does represent an energy barrier, but you get thinner and thinner and thinner, you get a quantum mechanical phenomenon called tunneling, where it shouldn't actually be allowed to trespass that border and go across it, but it does anyways. And we're getting there. Our transistors are so small that tunneling current, this leakage current, becomes non-trivial, so we can't go any smaller. So what will you guys do? We're out of time. So what will you do in 2019 and forward to fix this problem? How will we continue to have smaller, more awesome, more amazing electronics? It's going to require creative solutions from graduate students, probably, and not their PhD advisors. Okay, have a nice rest of your day.